Hello, today lecture is about Sharpless asymmetric epoxidation. Okay, we have know about what is this epoxidation? We know that formation of epoxides are generally known as formation of epoxides are mostly known as epoxidation. Okay, so this is called epoxidation, formation of epoxides. So we know this in our earlier cases, in the earlier classes also we have discussed about this epoxidation. So epoxides are formed by reacting these alkenes or olefinic compounds. So let's say these compounds, say one here, Cs by using this uh, peroxide, or you can say peracid. So by reacting these alkenes, olefinic compounds, and we got up this epoxide. Okay. So we discussed this earlier also. So here epoxide is got there. We got a cis from cis alkane. We got cis epoxide. Okay. And similarly, if you react trans alkene, then we got this trans alkane. Then we got this trans. Okay. Trans we get similar same case peroxide, which are using as is peroxide or peracid. Then we got this trans product. Okay, here is R, so here O R is trans product. Okay, so what I want to say is that epoxidation reactions by reacting alkenes or olefinic compounds with peroxide or peracid, we got epoxide. From cis we got cis epoxide. From trans we got trans epoxide. Okay, trans alkene will give trans epoxide. So it is the epoxidation reaction is regiospecific. Okay, regiospecific. That they give only one product. Specific. Okay, regiospecific. So it gives cis will give cis, trans will give trans, like that. But if certain catalysts are used, then we can get if certain catalyst is used, then we can get different epoxides which are enantiomer, different epoxides which are enantiomer may be obtained also. So we'll come to Sharpless asymmetric epoxidation. So here generally I'm giving one is what is the epoxidation, how epoxides are formed like that. So they are regiospecific. So cis will get cis alkane will give cis epoxide, trans alkane will give trans epoxide. So Sharpless asymmetric epoxide is generally say allyl alcohols. So let's say this allyl alcohol. Let's say R1, R2, R3, R4. So when you react with some catalyst, okay, so allyl alcohols, this is allylic alcohols. Okay, they can be either primary or secondary. So you got a epoxide. So O here. Okay, this is R4 OS, and this is R3, R1, R2 like this. So epoxides. So you can say we can say 1, 2, 3, 2, 3 epoxy alcohol, 2, 3 epoxy alcohol. So I'm repeating again. Okay, Sharpless asymmetric epoxidation takes place when allyl alcohols either may be primary or secondary reacts with certain catalyst. So they have to give 2, 3 epoxy alcohol. Similarly, so here Sharpless epoxidation, asymmetric epoxidation is a conversion of, I write down here, conversion of say primary or secondary allyl alcohols into 2, 3 epoxy alcohols. Okay, so here Sharpless asymmetric epoxidation, you can simply SAE, Sharpless asymmetric epoxidation. So it takes place conversion of 1 degree or primary or secondary alcohols into 2,3 epoxy alcohol. And second one is that the reaction is enantioselective. 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 There is only one isomer. Enantiomer is formed. Enantioselective. There is only one enantiomer is produced. Only one enantiomer is formed. Only one enantiomer is produced. Okay, is produced. So here by using different catalysts, the enantiomer form maybe depends. The enantiomer form is depends on the nature of the catalyst used. Enantiomer does form okay, depends on the nature of the catalyst, depends on the stereochemistry or on the nature of the catalyst, on the stereochemistry or nature of the catalyst, stereochemistry of the catalyst use. Okay, so yeah, I'm repeating again. So yeah, the Sharpless asymmetric epoxidation takes place when the conversion of primary or secondary allyl alcohols into this epoxy 2,3 epoxy alcohols. So here reaction is enantioselective, highly enantioselective, giving only one enantiomer. Is produced. The enantiomer form depends on the stereochemistry of the catalyst. So it depends on the catalyst used. So here does I write down here does Sharpless asymmetric epoxidation refers to the highly enantioselective method for the asymmetric epoxidation of, so we can write down here. So does the Sharpless asymmetric epoxidation refers to the highly enantioselective epoxidation of selective method, or you can say selective method for epoxidation of or we can say like asymmetric epoxidation of for asymmetric epoxidation of say non-chiral, okay, epoxidation of non-chiral. These are allyl alcohols, non-chiral allyl alcohols are substrated by using this tertiary butyl hydroperoxide, tertiary butyl hydroperoxide. You can write simply as you can write tertiary butyl TBHP, tertiary butyl hydroperoxide in presence of plus or negative, plus or positive or negative diethyl tartarate, you can say DET, okay, DET, you can positive or negative diethyl tartarate and titanium dicalcitrate and titanium isoproposite and titanium isoproposite this is titanium OPR3 OPR4 isoproposite, which as catalyst together they are used to be as catalyst. Okay, so catalysis is between these two, that and titanium isoproposite together, they form the catalyst. So I am repeating again, Sharpless asymmetric epoxidation refers to the highly enantioslated method for asymmetric epoxidation of non-current alcohols by using tertiary butyl hydroperoxide, TBSP. Tertiary butyl hydroperoxide is like this. BuO is okay. Tertiary butyl hydroperoxide, TBSP. So this is the oxidizing agent in presence of the catalyst, that is that and the titanium isoproposite, they are the catalyst. Okay. So here I write down the Sharpless asymmetric epoxidation. The TBP is used, TBSP. Okay, tertiary butyl hydroperoxide is used as the oxidizing agent, or you can say oxidizing agent, or you can say epoxidizing agent. TBP is used as this one, TBP is, so I have written here earlier. Okay, then the catalyst is the titanium isoproposite is titanium isoproposite and that diethyl tartarate. Okay, and that diethyl tartarate, and here DCM dichloromethane is used as solvent, and at minus 20 degree temperature. Okay, it's very low temperature, so reaction takes place like this. So the use of diethyl tartarate can yield different enantiomer. So the use of plus DET or minus DET, diethyl tartarate, can produce will gives different enantiomers. Okay, different enantiomers. So here I am repeating again that the Sharpless asymmetric epoxidation, tertiary butyl hydroperoxide is used as the oxidizing agent, and the catalyst is combination of titanium isoproposite and diethyl tartarate, and dichloromethane is used as solvent and minus 20 degrees Celsius, depending on the nature of the catalyst, plus or minus. So different enantiomers are obtained. So let's see the reaction. Okay, how the reaction takes place. So I'll read the scheme of the reactions. So here, scheme of the reaction. So we have this allyl alcohol. Okay, OH like this. And then we can have this R1, R2. Okay. Then we have this. We can write TBBSP, tertiary butyl hydroperoxide, in presence of dichloromethane, and then at titanium isoproposite at minus 20 degrees Celsius. Okay, so you can have two types of reactions will take place. So here we can have, if you use this catalyst minus L minus plus, that diethyl tartarate, or if you use another one, use D minus diethyl tartarate. You can say positive and negative tartarate. So we will get two products. So So you can get two products. When you use this diethyl tartarate, positive tartarate, then you get a product of one. Okay, here O, then let's say this R1, let's say this R3, okay, here R3, then here we can get this one. This is allyl alcohol type OH, then we have this and this R1 and R2. Okay, similarly, let's say this is A product A, and similarly you can have another product here like this. So here we can have R3 and we can have OH. Similarly here R1 and this another one is R2. Okay, so we got this, let's say the product B. Okay, so we have these two are A and B are enantiomeric epoxy alcohols. They are enantiomeric epoxy alcohols. So here it takes place when we use the L positive diethyl tartarate, then with this oxidizing agent, this tertiary butyl hydroperoxide OOH. These are OOH will take from OOH will take from. So here we take from the upper side. Take from the upper side. Okay. Or if you use this negative diethyl tartarate, then this attack from OOH OBT will attack from the top, this from the bottom side. Okay. So I'm repeating again. If you use the negative positive diethyl, so attacks oxidizing agent attacks from the top side. Okay, top side. If you use positive diethyl tartarate, and if you use negative diethyl tartarate, then it attacks this oxidizing agent. That's DPSP attacks from the bottom side. Okay, so that's why we got different products from the bottom side. So these are got A or D depending on the nature of the attacks. Okay, so I'm repeating again. So here, when you have this allylic, this allyl alcohol, when it reacts with the tertiary butyl hydroperoxide, if the hydroperoxide in presence of positive diethyl tartarate, it attacks from the top side, so it gives this epoxide A. And if you use the negative diethyl tartarate, then oxidizing agent, the tertiary butyl hydroperoxide attacks from the bottom side. So we got a different two products, but these two are the products A and the B are enantiomeric epoxy alcohols being obtained by using positive and negative tartarate. So I'm writing here again. Okay, so here so summarizing here, Sharpless asymmetric epoxidation from we got two products. Count the products. So I have the products A, the product A and the B are enantiomeric these epoxy alcohols, they are enantiomeric epoxy alcohols being obtained by use of, say, one is positive diethyl tartarate and negative diethyl tartarate respectively. Okay, A is obtained from positive diethyl tartarate and B is obtained from negative diethyl tartarate. You can summarize like this. Okay, then the epoxidizing agent is the epoxidizing agent, that is the oxidizing agent, tertiary butyl hydroperoxides, and this agent, okay, oxidizing agent, tertiary butyl hydroperoxide attacks attacks from the top side, okay, from the top side. If positive diethyl tartarate is used to give the compound A, the product A. Okay. Similarly, if negative diethyl tartarate is used, then oxidizing agent PBSP, tertiary hydroperoxide, attacks from the bottom side, to give the product B. Okay, so this way we got one attack from the minus or negative diethyl tartarate used, then we done TBSP attack from the bottom side to get B, and if the positive DAT used, so depending on the nature of the catalyst, so you get TPSP attacks from the top to get the A. So depending on the nature of the catalyst, you got these two enantiomer product. This method of is used highly in the wide scope, highly used, but the precise mechanism is unclear. Okay, the precise mechanism of the reaction is unclear. We have highly used. This reaction is used by this scientist Carl Berry, Sharpless. The name of this Sharpless, which is scientist which introduced this Sharpless asymmetric epoxidation, is done by this Carl Berry Sharpless. So he got Nobel Prize. He received the Nobel Prize in these reactions in 2001. Okay, Nobel Prize in 2001 due to his work. So many can be applied. Many reactions, many products can be applied by using this technique. Okay. So here, what is diethyl tartarate? So we have the positive diethyl tartarate is natural. So here you can say the structure of this. Okay, this is ethyl group. Then this is okay, let's say this is this is ethyl group. Okay, then we have this, then we have another one, this. Okay, so here OH is this side, then hydrogen here, then here OH is this side, hydrogen here. So we then this is said to be positive diethyl tartarate, or you can say RR, here RR, diethyl tartarate, okay. So it is natural product. So here you can say L positive DET. Okay, this is natural obtained from natural tartaric acid. Is obtained from natural tartaric acid. Another one is said -1. Only position of this OH is different. Okay, this is ethyl group. Then here difference between this, here hydrogen OH here, and then here hydrogen, here is OH. What is the difference is position of this chiral center here. These two are chiral center. So here difference between these two are here. So here is negative SS. Okay, diethyl tartarate. Okay, these are unnatural, not available in the nature. So it is also commonly we can say D negative DET, diethyl tartarate. So it is unnatural. So if you use negative DET, we got a product B. If you use positive DET, we got a product A. So this is about depending on the catalyst of this thing, along with this titanium isoproposite is used. So along with this, together this that and together this catalyst. Okay, they use different, using this catalyst they got a different product. So this is about this Sharpless asymmetric epoxidation. So today I will wind up here. Okay. Now to next I will take another oxidation. Okay. So I will wind up here.